So in our first lectures on chapter 23, we talked about the ray model of light and we looked at reflection. And now we're going to look at refraction. So the purpose of this lecture is to understand refraction and also understand the law of refraction, which is Snell's law. And then in future videos, we'll talk about total internal reflection and then also lenses, which are really devices that we've harnessed refraction and used them in order to, for some purpose that we want to use them for. So let's talk about the idea of refraction. So we know that light from our ray model travels in straight lines, but when it interacts with some kind of medium, then the path of that straight line can change. And the reason that it's changing is because the speed of light in that medium is changed. So if c is the speed of light in a vacuum, so it's right here. So this is the speed of light. Right here. And v is the speed of light in a medium. So when I say in a medium, that means whatever transparent thing we're talking about. Is it glass? Is it water? So somehow that light is transmitting through. It's transparent, but it's at a different speed. And we say that the index of refraction is that ratio. So if you look over here at the table, there are different indices of refraction. So for a vacuum, it would be, as we expect, it would be 1, because c is the speed of light in a vacuum, and if v is equal to c, then we have c over c, which is 1. It turns out in air, it's a little above 1, it's 1.003. Well, a lot of times in our problems, we approximate it to be 1. Another one to take note of is water. It's about 1.33. And then a lot of times in glass, it depends on what type of glass, but in general, it's about 1.5 around there. So here's a number of glasses. And then we have plastics and acrylics, also about 1.5. And then ranging to diamond is like 2.42. So we see here that as the speed of light, it's going to be, as v gets slower and slower, or shorter and shorter, or smaller and smaller, then the index of refraction increases. So the greater the index of refraction, the smaller the speed of light in that medium. Now, I want to make one little note that really the speed of light doesn't change. But why are we saying that the speed of light in this medium changes? Well, what's really happening, if you remember, we talked about light being an electromagnetic wave. So here's light. And then light comes and it interacts with an atom in the medium. And then afterwards, that atom is going to gain some energy, or it's going to start moving. And then, because it's moving, remember from our discussion of electromagnetic waves, that moving or oscillating electron is now going to release more light energy to the next. So it's not really that light in between here, it's not that it's traveling in a different speed, but it's just now interacting with all these atoms along the way. So you can imagine if you walk at the same speed between, say, you're at a fair or something, and you, like a state fair or some event, and you go and you walk at your same speed between different activities, but then you stop and spend a little time at each activity, well, your time to get across the whole venue or the fair is going to be slowed down. You're still walking at the same speed, it's just you're interacting more at different places. And that's kind of what's happening at the atomic level with the light and the atoms. So we have this idea that light travels at different speeds, and as a consequence, what we see is that light that actually bends. So what happens is that the light is going to travel in such a way as to minimize the not the total path, but the time that it takes for the light to travel through the medium. So here's what we find just from experiment empirically. This is Snell's law, that if, again, we're dealing with an angle relative to the normal, and we measure this theta 1 is relative to that. So here, notice here on the left we have a source. The light ray comes in and then it hits the medium, water, just higher density, higher index of refraction, and then the ray then gets bent towards the normal, and that's the refracted ray over there. If I had a source in the higher density medium, then it goes up to the interface, and then we see that it's bent away from the normal. And that law of refraction, Snell's law, can be written like this. If N1 is the index of refraction in the first medium, then N1 times the sine of the angle theta 1 between the incident ray and the normal, that is equal to N2 times sine of theta 2, which are the index of refraction and the angle in the medium where it's traveling to. So then we see that the light can travel. Now, notice here as well, there's also this reflected ray. So it turns out when light interacts with this interface, there's also a surface. And so there's going to be a bit of energy that's reflected. And the same thing down here. You're going to have some reflection. So the light that actually is transmitted is going to be a little bit less than the incident ray that goes in. So if we look at Snell's law of refraction, from our experience, this is why things look just a little bit odd, say when we're submerged in water or something like that. So if you look at this in diagram A, you see that the person in the water looks to be shorter, has very short legs compared to the rest of their body or torso. And we can kind of see by looking at the rays what's happening here. If you look at the person who is in the water, light that's coming from the bottom of her feet, if we imagine a normal here, light that comes from her feet are going to have some theta 1 here. And now because we're going to a lower density or lower index of refraction, theta 2 is going to be lower, or greater. And so that light is going to bend away, and then you see that light going to this observer on the beach. Well, to that observer on the beach, remember our brain and our eyes say, hey, light travels in a straight line. So once again, the light will be traced back by our eyes and our brain, and then it will appear to that person that this person's feet are right here. So instead of the length here, then the apparent length will be right here is what it appears to be. and it actually makes the person look shorter. So we actually see, if you look at somebody who's wearing glasses, for example, you may notice, especially if they're nearsighted, you may notice that you can actually see an image of the side of their face in their glasses that is smaller than what their actual width, and that is that's due to refraction. And if we were to have, say, a block of glass, for example, and it's in air, as in this diagram, we see that the angle of refraction is going to make, or there's going to be a bending of the light. So here, notice that we have a ray that's coming in at 60 degrees to the normal. So again, here's a normal. It's always perpendicular to the surface. And at that point, theta A is, the ray is bent towards the normal, and we have theta A. Now notice from the geometry, these are alternate interior angles. So this is the same angle here and there. Well, then the question is, when it bends away, we have theta B, and it goes out. What is theta B? Well, Snell's law tells us that n1 sine theta 1 is equal to n2 sine theta 2. So let's call air, this is n1, and then the glass is n2, and we go back to n1. So for the going in, then we have n1 sine 60 degrees is equal to n2 sine, and instead of theta 2, I'm going to put what's labeled there, theta A. Now I look at the refraction at this interface over here. So here I'm going from glass to air. So now my starting, instead of n1 sine theta 1, I have the incoming, which would be n2 sine theta A, and that's equal on this side to n1 sine theta B. So notice here that we have n2 sine theta A both. So we could actually set those equal to each other in this equation, and we end up with n1 sine 60 degrees is equal to n1 sine theta B. Theta sub B, well, the solution to that is theta to B is equal to 60 degrees. So it turns out that this angle here is 60 degrees. However, what's happened here, because of the refraction, the point, what light came at this point has been shifted over by this amount. Let's call this D. And if T is the thickness, I can use the geometry here, actually trig, and I see this triangle here, I'll draw it bigger, is theta A, and this is D. It's right angle. I'm looking at this triangle here. And the thickness is T. So that tells me that tan theta A is equal to D over T. So I can figure out how much this image is shifted over by figuring out what theta A is, and then also knowing the thickness of the glass. Okay, in the next video we'll talk about total internal reflection, but that is Snell's law and refraction.